Hi, everybody. I'm Professor Sara Seager from the Massachusetts Institute of Technology. I hope you've been enjoying the school, and I'm looking forward to getting your questions soon. I'm here today to talk to you about biosignature gases in exoplanet atmospheres. I'm just starting out with this picture of our night sky, so you can see the concept that there are so many stars out there. We know there are a lot of rocky planets, and we like to speculate that there must be life on some of them. Well, a few billion years ago, something amazing happened on our planet. The humble cyanobacteria discovered how to capture energy via photosynthesis. And as a result, the cyanobacteria gave off oxygen gas as a waste product. Over time, oxygen eventually accumulated and filled our Earth's atmosphere to 20% by volume. I like to call that the cyanobacteria re-engineered our atmosphere. Today, without vegetation and without photosynthetic bacteria, Earth's atmosphere would have virtually no oxygen. I love to imagine there's an intelligent civilization on a planet orbiting a nearby star with the kind of telescopes we're hoping to build, and that they're looking back at Earth and they see oxygen. And they will be thinking, wow, that is so unusual, because oxygen is a highly reactive gas, and it shouldn't be present unless it's continually replenished. The story does get a lot more complicated, though, because there are a lot of different scenarios people think of for many gases where they may be produced by life, but there may also be what we call false positive scenarios to produce those gases. So I'm going to give you an introduction to biosignature gases. Then I'll talk about telescopes. Then I will talk about some of my own work on biosignature gases. Here's a quote I found from a book. It was a report about the limits to organic life in planetary systems. And this quote says, "Nothing would be more tragic in the exploration of space than to encounter alien life and fail to recognize it." So as I said already, Earth has only had significant atmospheric oxygen for part of its lifetime for the past billion years or so. And this quote has been my guiding principle in my research, because I'm constantly asking myself what kind of gases might be produced by life on another world. There are literally so many gases out there. There are thousands of gases produced by life. And this really intriguing thing I came upon, thanks to a question from a friend, is that if we think about our own Earth's atmosphere and all the gases in our Earth's atmosphere, each one of the gases that is present to the part per trillion level or greater is actually produced by life on Earth. Although most of the gases have a dominant source that is not life, they are all produced by life. Even ozone is produced inside some cells. Here I divided them into Earth's atmospheric inventory, anthropogenic gases that are just made by humans, and I forgot to say, except for the noble gases, which don't interact much and are not produced by life. So I do have a way to organize these gases, any of the gases or the thousands of gases, and I wanted to just share that with you for a moment. So starting with oxygen, I do think oxygen is the favorite biosignature gas. It is so reactive, it shouldn't be in an atmosphere unless it's continually produced. That said, astronomers, astrophysicists, astrobiologists are all trying to find all the false positive chemistry scenarios and corroborating observables. And this kind of has been going on for a number of years, where one research group will think about a way to produce oxygen that doesn't have anything to do with life. And usually a year or two later, another group finds that that concept is incorrect. And it kind of goes back and forth. There still are a couple of scenarios where oxygen conceivably can be produced without life. There's a set of small gases, including methane, nitrous oxide, and other simple gases that people study as biosignature gases. These gases are produced by microbes, which may be simple single-celled life. But each of the gases in this category has a false positive source, because the way I like to think about it is nature has the same chemicals to work with that life does. So for example, methane is produced by methanogens. Some of the methanogens live at the bottom of the ocean, where they are using carbon dioxide that's been mixed down from the atmosphere and hydrogen that comes off of rocks, cracked rocks, and hot water going over the rocks releases hydrogen. And there's a chemical potential energy there that life catalyzes to make the reaction happen so it can give off energy. And it ends up producing methane and water. But at the same time, just somewhere else on Earth, that same reaction that requires a catalyst will just happen naturally. And indeed, in mid-ocean ridges also produce methane gas. So this sort of set of common, simple molecules that we like to think about as being biosignature gases because life on Earth makes them, they're also just full of false positives. There's another set of gases that are more complex. And some gases in this category that have been studied include dimethyl sulfide and methyl chloride. And these gases, they're not made by life exploiting simple chemical potential energy gradients, but instead they're made sometimes for unknown reasons, or they could be made for stress or signaling, hormones for other purposes. Now, this set of molecules rarely has false positives because they're complex, they're hard to make, and they have no reason to just be naturally made by some kind of geophysics or geochemistry. At the same time, this complex category of molecules, they're usually made in very small quantities on Earth. And it's tough to argue about a source of complex molecules that would just, for some reason, produce enough of it to accumulate in an atmosphere. So life on our own Earth actually produces thousands of gases, actually. So many gases, although most are in tiny quantities. My team actually works with all of these gases, and I'll come back to this towards the end of my lecture. We do create this filter here is indicating algorithms we use to try to work through literally every possible gas. We want to, going back to that quote, increase our chances of being able to identify alien life. If we find a gas that doesn't belong, we'd like to have the ability to understand what category it fits in, what are the possibilities that it might be made by life of any kind. To summarize the first part of my lecture, I'll give you my definition of a biosignature gas. A biosignature gas is a gas that is produced by life that can accumulate in an exoplanet atmosphere to levels that we can potentially detect using our telescopes. A biosignature gas is not detection of life itself. Rather, a biosignature gas is a sign of life. Now I'm going to move on to part 2 of my lecture, where I'll discuss next generation telescopes. I divide these into 2 categories, transits and direct imaging. And yes, I will go through some main points in each of these categories. First, though, let's talk about our Earth. In principle, Earth shouldn't be so hard to find, discover, detect, study. In practice, the problem is that a planet like Earth is right next to a big, bright, massive star like our sun. And it's just the proximity to the star that creates such a huge problem for detection. Now, our Earth is 100 times smaller than the sun. That's 10,000 times smaller in area. Our Earth is 300,000 times less massive than our sun. And our Earth is 10 billion times fainter than our sun. If I was with you, I would ask you, is your favorite planet finding technique? One that involves planet size or area? That's transits. One that involves planet mass? And that would be radial velocity. Or one that involves planet brightness? Now, I'm sure that in other lectures you have heard about each of these or will hear about each of these in some detail. But let's just say, and so you may already know the answer, that for today, the most popular way that we find planets is by the planet size or by the planet area. And in this case, we'll talk about transits. And I'll go through this a little quickly because I'm thinking this was covered in some other lectures. Well, the transiting planet is one that goes in front of the star, as seen from our telescopes. On the bottom, there's just a cartoon of the brightness of the star as a function of time. And on the top, that's just the artist's conception, because of course we don't have any stars we can spatially resolve like that other than our own sun. So the key takeaway here that is really important is that when the planet goes in front of the star, some of the starlight shines through the atmosphere. And we actually can tell what's in the planet atmosphere with very careful measurements by seeing which planet features from the planet atmosphere are imprinted on the stellar light. Typically, we will look at the star by itself and we look at the star during transit, and subtracting the two reveals the planetary atmosphere, the exoplanet atmosphere spectrum. I wanted to just have this for you because I'm going to come back to this a bit later. But we can think of the transit atmosphere signal strength. We can estimate that by the size of that. In this cartoon on the top left, you see the star in yellow, the planet in black, and the planet atmosphere is heavily exaggerated in blue. And the signal just relates to the area of the annulus, this blue annulus, compared to the area of the whole star. And typically, I like to think of the atmosphere as being a few scale heights. Here I just put 5 to just, for a nice round number. And to get this formula at the bottom, I literally just took the formula for the annulus divided by the area of the star. So you can work that out. The pi cancels, rp squared, that term ended up canceling because it's so small. And this is what we're left with. Well, the scale height, and hopefully you work through this in another lecture or at another time, but the scale height indicates how puffy the atmosphere is. And the scale height comes from, you can work this out yourself actually, if you take hydrostatic equilibrium and considering the ideal gas law, which is definitely valid in an exoplanet atmosphere. And if you take these two equations and work through them, you end up with this pressure equation on the left, where pressure at some altitude equals a pressure, we call it P0 just for some reference pressure, with this e to the minus z over h, where h is the scale height. And you have to work through the equations to get this definition of the scale height, but essentially it's Boltzmann's constants times temperature over the mean molecular mass times the surface gravity. And so the key takeaway here is that for hot planets or hot Jupiters, they're very big. Their atmospheres are hot, like 1,000, 2,000, or even hotter Kelvin. And they're hydrogen atmospheres. And so these scale heights can be several hundred kilometers. For our own planet Earth, our atmosphere is quite small. It's cold and it's high mean molecular mass. Our scale height's only 8 kilometers. But what's going to be relevant later is imagine a small planet, a rocky planet, maybe a bit bigger and more massive than Earth, that's able to hold on to a hydrogen atmosphere. Well, the mean molecular mass of a hydrogen atmosphere is about 2 as compared to the mean molecular mass of Earth's atmosphere, which if we think of molecular nitrogen is about 28. And so a hydrogen atmosphere is always puffier, according to the scale height and according to this synopsis. So I just have a couple of transmission spectra of hot Jupiters. Dozens of exoplanet atmospheres have been observed with transmission spectra. We use Hubble Space Telescope data. We use complicated computer codes to both simulate and interpret data. And this is just showing you the transit depth on the left. You can look how many decimal places this is going. It's really quite incredible. It's 1, 2, 3, 4 decimal places. So this is like a few parts per 10,000. This is wavelength in microns. The solid curves are models, and these points with error bars are real data. You can ignore the left part of the diagram. On the right here is a giant water feature. And essentially what you're looking at is the planet. The planet, essentially, let me just back up a little here. Essentially, I want you to imagine the planet with no atmosphere. That planet is a certain size. A planet with an atmosphere will appear much larger. And it turns out there are some wavelengths where the atmosphere is mostly transparent. And so the planet may appear to not, the planet will not have any atmosphere features. There are other wavelengths where the atmosphere is very opaque and blocks out more starlight, thus making the planet appear a tiny bit larger. And in this figure, what you're seeing is the transit depth. So the planet looks a tiny bit larger where there is significant absorption. In this case, this happens to be a water vapor absorption feature. Here's another one of my favorite plots. This is it was WASP 39b. We call this a hot Saturn exoplanet with a very, very low density. But the point here is that today we use the Hubble Space Telescope to study hot giant exoplanet atmospheres and a few other planets. But in the future, we're planning to use the James Webb Space Telescope to push down to small rocky exoplanet atmospheres. So all of the work that people have been doing over the last decade, 2 decades or so, using Hubble, we're going to try to repeat all of that on small rocky worlds. Now, I forgot to mention that the James Webb Space Telescope, in observing transmission spectra, must focus on M-dwarf host stars for small rocky planets, because a small rocky planet atmosphere against the backdrop of a sun-like star is just too small for us to be able to detect. And here is showing you tests, this mission test, we call that our finder scope. I also put a note to say, I hope that there are rocky planets with hydrogen-dominated atmospheres, because it's going to be very, very hard to make these observations with the James Webb Space Telescope. And the hydrogen atmospheres, because of their bigger scale height compared to atmospheres that are made of carbon dioxide or nitrogen, the hydrogen atmospheres will just be bigger. So we have a lot of hopes pinned on the James Webb Space Telescope. We're not quite sure how well it can do, what its noise floor is. I can assure you there are a lot of proposals that have been put in to use the James Webb Space Telescope for this purpose. This is just an image showing you some numbers of our Earth and Sun, and our Earth and TRAPPIST-1. So for our Earth and Sun, the planet to star area ratio is 1 part in 10,000. And using the equation on the slide, a few slides back, I estimate the atmosphere, the area of the atmosphere compared to the area of a star for an Earth-Sun analog would be 1 part in 50 million, which is definitely not detectable with the James Webb Space Telescope. On the right, I'm showing you an Earth-sized planet orbiting, transiting TRAPPIST-1. In this case, the planet to star area ratio is 1 part in 100. The atmosphere area to the star area is 1 part in 10,000. And I showed you before we were actually able to do 1 part in 10,000 spectroscopy, transmission spectroscopy using Hubble. So with the James Webb, hopefully we'll be able to do that. Hopefully the TRAPPIST planets have atmospheres and we can study them. So transits from space, we have the James Webb Space Telescope, and the TRAPPIST-1 planets are key. I'm now going to move on to direct imaging, because transits are only the first part of a very long story. Transits are limited to planets with a fortuitous alignment. The planet and star have to be lined up just so in order for the planet to show, the star to show that the planet is transiting. Imagine for a moment if the planet is orbiting in the plane of the sky, it won't be going in front of the star. Direct imaging is an umbrella term for all methods that block out the starlight so we can see the planet directly. In this case, you can imagine a giant screen that blocks out the starlight so we can see the planets. This screen can actually be outside the telescope, and I'll talk a bit more about that in a bit. Or the screen can, this blocking device can be inside the telescope. Inside the telescope, it's called a coronagraph. So there's a really huge field in direct imaging and designing the external screen that we call starshade, or the internal screen internal blocking device we call a coronagraph. And I want to explain to you basically the heart of the whole matter. Now, let's imagine it's a giant screen in space with its own spacecraft lined up with a space telescope. It actually can't be a giant circle because the background star, the star that you're trying to block out, you're actually not going to end up blocking it out because of diffraction. Light can act like a wave, and it will bend or diffract around the outside edges of the big screen in space. And the same applies to the coronagraph on the inside of the telescope. What you'll end up seeing in your image is ripples, like on the top right. Although here I've made this on a logarithmic scale, so it shows up more clearly. But this first ripple, this first so-called airy ring, in terms of an Earth-like planet orbiting a sun-like star, that first airy ring would be 100,000 times brighter than the type of planet you'd be looking for. So the whole field of direct imaging, whether it's for coronagraphs or for the starshade, it relies on having a very special shape. And in this case, you can see on the left a special shape like a giant star shape. In this case, the light will diffract around the edges in such a way to cancel each other out. And in this way, the image becomes very dark. And you can think of it as all the light being pushed to the outer edges. Now, the story is much more complicated than what I described, but that's enough for us to take this tour of where we're at and where we're going with direct imaging. On this figure, I'm going to show this figure many times, and each time I'll talk about a different telescope that has a higher sensitivity. So on the left, I'm showing you the flux ratio of the planet to the host star. On the bottom, it's showing you separation in arc seconds. I suppose this is for a system at 10 parsecs away. You can see here our Earth, an Earth twin. Wow, this is just incredible. Our Earth is 10 billion times fainter than our sun for the Earth in reflected light. So Earth is down here at 10 to the minus 10, and at 10 parsecs, it would be 0.1 arc seconds away. So the challenge is in not just blocking out the starlight, but in blocking it out so that we can see very close to the star. Jupiter would be out here, about 10 to the minus 9 contrast, and its separation at 10 parsecs would be 0.5 arc seconds. Now, what you're seeing on the top here, the symbols are planets. These are directly imaged planets. They're actually, look at this, their contrast, it's still small, but way bigger than what for cold solar system planets. These are hot, massive planets or young planets that have their own energy from when they first formed, leftover gravitational potential energy that's still working its way out. These sensitivity curves here are for different telescopes. HST NICMOS, this is, looks like it's James Webb Space Telescope NIRCam. We have HST STIS, Gemini, Giant Planet Imager, VLT Sphere. So for today, we're limited to this top right corner here, planets relatively far from the star that have their own luminosity, but that are nowhere near what we require to directly image for solar system type objects. So current ground-based telescopes, 8-meter class telescopes with special instruments, search for massive, hot, young, self-luminous giant exoplanets. What's amazing is that there are the extremely large telescopes, 30-meter telescope, Giant Magellan telescope, European extremely large telescope, that are now under construction, that with the right instrumentation may obtain planet-star flux ratios shown by this giant green box on the left. Because they're so big, they can get the angular separation that we need, reaching out to habitable zone planets. And the contrasts 10 to the minus 7 to 10 to the minus 8 are actually good enough to reach habitable zone planets orbiting M-dwarf stars. And these planets would be shining in reflected light in the near infrared, like JHK in photometry from these large ground-based telescopes. And what's really exciting is that we already have a planet. I put a giant P here to show you about where it is. It would be at 0.04, which is just off the edge of this plot, for Proxima Centauri b, an Earth mass planet that is not transiting, but is known to be orbiting our very nearest star, Proxima Centauri. And we think that these new giant telescopes can survey about 100 or so M-dwarf stars to look for planets. And if we can see the planets in direct imaging, we can also study their atmospheres. Our next opportunity will be a space telescope. It was called WFIRST. It's been renamed to the Nancy Grace Roman Telescope. Roman is a 2.4 meter on-axis telescope. It will have a coronagraph instrument. That's a device internal to the telescope to block out starlight. This coronagraph instrument, it's a tech demo. And it's a tech demo, and yeah, we're just excited to get the ball rolling, so to speak, on coronagraphs on telescopes in space. One of my favorite projects, we call it Starshade Rendezvous Mission. Starshade would be a giant specially shaped screen in space. It would be built and launched separately to the Roman Space Telescope. It would have its own spacecraft, and it would meet up on orbit, which is why we called it Rendezvous. The Starshade working together with the Roman Space Telescope could discover a handful of exo-Earths. We would literally focus our time and our efforts on 8 to 12 bright sun-like stars. We could discover a handful of exo-Earths and kind of dozens of planets in general. And Starshade Rendezvous would have to be down here. We would design Starshade so that it could be sensitive to an Earth, although only around a small number of stars. Here's a curve showing you where the Roman chronographic instrument might reach to. Now, in the United States, we have been studying two more powerful missions. These studies are now completed, and if you want to Google these names, you can come across the final reports. And there's two different ones. But by and large, they have to be able to reach down to these contrasts in order to be able to find so many planets. And the white circles on here are from a simulation from one of these telescopes called HABEX, Habitable Exoplanet Observatory. This telescope would be a 4-meter diameter telescope. And our favorite design was one that is off-axis, which has a coronagraph and also a starshade. Because the coronagraph is inside the telescope, and the telescope can move around quickly from target to target. But the chronograph's actually quite inefficient because you can only block out the starlight over a very small wavelength range. The starshade, on the other hand, can cover all wavelength ranges, but it's very slow because for each new target star, the starshade and its spacecraft would have to move across the sky. It would take a week or two to line up with the next target star. So the concept with HABEX is to have both. The chronograph helps discover planets effectively, and the starshade would be ideal for spectroscopy of those planets. Now, there's a range of mission options. I'm not going to go through all of them, but I wanted to flash this up for anyone who cared to know some of the details of the HABEX observatory. Our spectroscopy, which is related to looking for biosignature gases, would be somewhat low resolution, 140 from 450 to 1,000 nanometers. And it would be smaller for the infrared, 1 to 1.8 microns, and also smaller for the blue and UV. So I'm going to wrap up this part of my lecture by talking about Starshade, a giant specially shaped screen that can launch together with the Space Telescope. The petals would unfurl from their stowed position, and the central truss would open in such a way that the petals will then snap into place. This starshade would be tens of meters in diameter and would have to formation fly tens of thousands of kilometers from its space telescope. And the starshade and telescope would have to line up almost like perfectly, literally, to block out the starlight so we can see the planets directly. Now, Starshade has been ongoing for its technology development in earnest since around, let's say, 2010. And before that time, believe it or not, Starshade was first invented, let's call it, in the 1960s. And each decade, some group revisited Starshade in some form. Until today, we do believe that we can build it. There's myself and some team members. with one of the petals of starshade. Look how big starshade petals have to be and how specially shaped and how pointy that sharp tip is. The goal is to be ready for a possible mission opportunity later in the decade. This petal, by the way, well, you can ask me more questions about it later if you would like to know a bit more. Here's one of the engineers at NASA's Jet Propulsion Laboratory in California, United States of America, showing you some scale models, smaller scale models of the starshade, thinking about how we would still it and deploy it. So that summarizes this part of my talk. Each of these telescopes has a transits, which we will do with the James Webb Space Telescope, direct imaging, which on the ground will use the new ground-based extremely large ground-based telescopes. In space are just mission concepts right now, but we hope that one will be selected to be built and launched in the next decade or two. Each of these methods already has a known planet or a set of planets that we can study. Now, before I end this part of my talk, I do have something to show you. And I was wondering if you'd like to guess what this is. This actually is a 1% scale starshade. I have it's not showing up that well because I have like the fake background thing on. But this was used actually in tests to demonstrate that starshade can actually work in the environment. And I will save the rest for, you can ask me more about starshade during the Q&A. Now I'm going to move to part 3 of my lecture. But first, I just want to summarize where we're at. We've talked about what a biosignature gas is. And before in part 2, I walked through the different options for telescopes. We have the James Webb Space Telescope, which is launching later this year in 2021. We have the new giant telescopes now under construction. And there are many concepts and technology development ongoing for both the internal coronagraph and the external occulter that we call the starshade. So next, I'm going to talk about new thoughts on biosignature gases. And here, it's not necessarily a pretty picture. I mean, I've told you we know how to study exoplanet atmospheres. You've heard before in the school that rocky planets are common. We're going to have all these wonderful telescopes. But the reality is a little messy. So we do know that exoplanets are incredibly diverse. They come in all masses, sizes, orbits, and we expect this diversity to extend not just to the rocky planets themselves, but also to their atmospheres. Some may be volcanically dead. Others might have atmospheres with what we call cold trap. We could have water worlds or planets with a host star that has a lot of far ultraviolet radiation. They're going to be very old planets. And these planets may have very different kinds of atmospheres that we haven't yet anticipated. At the same time, we know of so many molecules. Life on Earth is producing thousands of them. And just to kind of, I went off on a big research endeavor to literally tabulate every single molecule that could be in gas phase at room temperature and pressure, or at the temperatures and pressures expected on the surfaces of planets, habitable planets, those planets that also have the right surface temperatures and pressures for liquid water. And we came up with a list of like 14,000, now it's actually up to 16,000 molecules. And we have algorithms that sort through all these molecules, dividing them into different categories, so we can be prepared to recognize biosignature gases of any kind. Now, it's not that I'm expecting, life produce one of these 16,000 very obscure molecules in some cases. It's kind of more of like a research drive to like fully understand, exhaustively understand, what are the possibilities out there? Because who's to say that a molecule that's not produced by life on Earth won't be produced by life elsewhere. And so actually the student, his name is Zhucheng Zan, he's just finishing his PhD thesis now. And he actually, I think he managed to mostly crack this problem. And I'm going to walk you through this figure about how we're sorting through all the molecules. First, we start up here in this triage phase, where we take the molecules in our database, we call it the all small molecules database. And we actually have to find out whether or not they have spectra. And by the way, most of them don't, it turns out. Like hundreds of them do, but not thousands of them. Then we put it through a spectra simulator, and we go through this pyramid asking ourselves, does the molecule have spectral features that we might be able to detect one day? Are these features distinguishable from other molecules that also have spectra? And we kind of go through this initial list of options, and many of the molecules get dropped because they have no significant spectral features that stand out from other molecules. So if they do survive this initial triage, we move on to this evaluation stage. And the key here, honestly, if there's one thing you can take away from my entire talk, it is that photochemistry is key for the survival of biosignature gases. And gases are actually quite easily destroyed, either through ultraviolet radiation destroying the molecule directly, or by the ultraviolet radiation destroying another molecule and creating a radical, such as the hydroxyl radical, OH, that in Earth's atmosphere, we call it the garbage eater of the atmosphere, because OH just destroys a lot of molecules. So this molecule can survive photochemistry. It's a good biosignature gas. And in my team's research, then we've been asking about each gas, is it produced by life on Earth? Does it have limited false positives? And if it kind of makes it through this whole triage phase, then we pursue it and we do detailed simulations. Now, we're not going to work through each gas one by one, because with 14,000, 16,000 gases, and one gas per student, that would take like 16,000 students. Instead, we're just doing categories of gases based on a fragment of the molecule that's called its functional group. That's a kind of longer story, but I just wanted you to have this bigger picture of how my team is exhaustively sorting through biosignature gases. Now, hopefully you've had another lecture that walks you through atmospheres, because understanding exoplanet atmospheres is key for biosignature gases. And essentially, we use a bunch of equations: conservation of energy, energy transport, hydrostatic equilibrium, and the ideal gas law, and then some kind of chemistry. And we put all of this together in a computer code to calculate layer by layer what are the abundances of each molecule in the atmosphere. And this cartoon in the background, it's showing you a planet. And it's showing you that geoflux, I just called it geoflux, like gases being produced by volcanoes. And it's showing you bioflux, like gases produced by life. And these gases are produced at some rate, emitted into the atmosphere, where they mix together along with all the other atmosphere components. But it's showing you that the gases are photochemically altered. And like, to capture all of this, honestly, that's about 2 or 3 years of work to understand the physics and chemistry behind it and how to operate computer codes. So if you want to work on biosignature gases, that's what it's going to take. And even with all these computer codes, there's a lot of buttons to push and knobs to tweak, and it's very complicated. And to add on top of this now, it's kind of standard in the field, although usually our data is not good enough to do this, to do what we call retrieval. That is, we want to simulate what an exoplanet atmosphere might look like with a given biosignature, set of biosignature gases and false positives. And we want to be able to, measure the amount of gas in an atmosphere by retrieving the information. And this is kind of complicated, but a simple way that I like to think about retrieval is starting with the concept of fitting a model, fitting data rather. You could imagine generating millions of models, hundreds of millions or billions or trillions of models, and only a subset of those will fit the data. And the subset of models that fit the data will tell you, based on those models, the temperature and pressure profiles, the abundances, it'll help constrain what the data can tell you. But you don't have time to run trillions of models. And so retrieval is an umbrella term for a procedure that lets you cleverly walk through parameter space. So you don't have to run all those models, but you just run ones that are judiciously chosen on the go. And here I'll just leave this for you. You can just, I put this up here just so you could read through it and get the general gist of it. So back to triage, I only picked one gas to talk about. In this lecture, it's all I have time for. We've worked through maybe 3 or 4 gases, and then we've also worked through giant classes of gases as well. And I'd be happy to answer some questions about that in the Q&A session. So the gas I chose to talk about is phosphine. Phosphorus is an essential element for all life on Earth. On Earth, it's actually used by life as phosphate. Because on a planet like Earth without hydrogen, without much hydrogen, phosphorus wants to go with oxygen, not with hydrogen. Sort of at first glance, phosphine appears to be almost completely absent from biology. And we found this, we got interested in phosphine partly through the triage process. And we realized by reading the literature that people didn't like phosphine as a gas associated with life. The sort of main concept was that there's no confirmed life-producing instances, and that phosphine gas is toxic and unstable. Well, it's true that the gas is toxic and unstable, and phosphine was indeed used as a chemical warfare agent in World War I. But this turns out to be true only in oxidized environments. In terms of no confirmed life-producing instances, you should know that we do not know exactly which species of life makes phosphine. It appears to be some kind of E. coli bacteria. But phosphine has been found in oxygen-free environments such as wetlands. And biologists have measured phosphine coming from bacteria, a mix of bacteria in anoxic bacteria in laboratory environments. So I like phosphine because, at least on Earth, it's only associated with biology, with humans making it as pesticides, for example, or with life in oxygen-free environments. And phosphine is very thermodynamically disfavored. It's inconceivable to think of like even a volcano being able to make phosphine because the amount of hydrogen, the temperatures and pressures just are not right for it. So we took phosphine after making it through our triage process and simulated what it would look like to the James Webb Space Telescope. The key thing we want to know is how much phosphine needs to be produced by life in order for it to accumulate against all of the sinks, the ways that phosphine can be destroyed. And so typically in the field of biosignature gases today, you'll see some kind of simulated data like I'm showing you here. So I'm now showing you transit depth. And this is for a 10 Earth mass planet that's 1.75 Earth radii with a 1 bar atmosphere, composed mostly of hydrogen. Because remember, so we've kind of cherry picked one of the most favorable cases possible to see if it's going to be at all feasible to think of looking for this biosignature gas with the James Webb Space Telescope. Now this figure is showing you transit depth in parts per million. And this is wavelength in microns. And these giant color blocks are for different instruments. This is all simulated data, and it shows you error bars as well. And what you're supposed to do is look at the difference between the two curves. One of them is without phosphine, this lower curve that's in blue. And this upper one is with phosphine. And this other one is with phosphine. And you can see like, wow, these two curves are actually quite different, especially at very specific wavelengths. But to get this level of difference, the bacteria making phosphine would literally have had to re-engineer the atmosphere, just like the cyanobacteria did on Earth so many billions of years ago. So we like phosphine because we have demonstrated phosphine can accumulate in an anoxic atmosphere, an atmosphere without oxygen. We like phosphine because on a rocky world like Earth, I just paused because we know our Earth is an oxidized environment, but on a planet like Earth, phosphine doesn't have false positives, and we can argue that on any rocky planet whose surface temperatures and pressures are suitable for liquid water, they're unsuitable for phosphine being formed by geochemical processes. Unfortunately, in our simulations where we ask ourselves how much phosphine do we need to produce to accumulate in the atmosphere to detectable levels, we need huge production rates. required on order of 10 to the 12. This is just like, this number probably doesn't mean much, but it's a big number. So considering some other gases we looked at, I'm going to, this kind of idea that's been formulating. It says at the bottom left, Ranjan et al. In PrEP. I'm showing you now biological surface flux. This is on a log scale for different gases, phosphine, isoprene, ammonia, and also for oxygen and methane. And the orange color is the global production levels here on Earth. And the blue is the simulations we've done for this favorable case of a planet with a hydrogen-dominated atmosphere orbiting a small M-dwarf star. And you can see that the blue bars are very big, that we do need life to re-engineer the atmosphere in order for us to have hopes of detecting biosignature gases. Now, I can't yet say if this is like universal, but what we're seeing is that these gases essentially need to accumulate to a level where the production rate exceeds the sink rate. So life has to be producing the gas faster than the gas can be destroyed by photochemical or other processes. And that's the kind of latest thinking in my team, which is good that we've thought about this and figured this out, but it's negative that we have to imagine that for whatever reason, life would be producing these gases. Now, I do want you to know that isoprene, it's a gas that on Earth, it's produced in as high quantities as methane is produced on Earth. And you might not have heard of isoprene. It's released from trees primarily and other vegetation. It's made by many, many different kinds of life on all branches of the phylogenetic tree. That one's obscure, and it is produced in huge quantities here on Earth. So we don't yet know what's really out there for us on other planets in terms of biosignature gases. So to summarize, biosignature gases are gases produced by life that may accumulate in an exoplanet atmosphere. The ideal biosignature gas has unique spectral features as compared to other gases and limited false positives. Biosignature gases are signs of life, not evidence of life itself. In general, in the field of astronomy, there's this fast-track search for habitable worlds, focusing on small planets transiting small red dwarf stars. And that's because our first chance at being able to study small rocky planet atmospheres for biosignature gases is the James Webb Space Telescope. This telescope is launching in 2021. Now, the jury is still out on how well the James Webb Space Telescope can do in terms of searching for biosignature gases. If there are rocky planets with hydrogen atmospheres, that's great news for us because the atmospheres will be puffy and it will be easier to detect gases of any kind. If rocky planets all have small, high mean molecular mass atmospheres, it could be tricky and we might not succeed in detecting biosignature gases with the James Webb Space Telescope. So in my talk, I also talked about future telescopes, the large ground-based telescopes now under construction, and space concepts for sophisticated starlight blocking techniques. The challenges for biosignature gases include that there are lots of false positives. We need very high biological gas production rates. And a point I hadn't mentioned yet, but wanted to leave you with is that the lower atmosphere is not well probed by transmission spectroscopy. So despite all of this, there's tremendous enthusiasm for studying exoplanet atmospheres and for thinking about biosignature gases. And I think it's just tremendous that we're the people, we're the first generation who can take this topic seriously, and that soon we will have real data on habitable planets transiting small stars, and that our future is really limited only by our own imaginations. Thank you for your attention, and I will see some of you at the question and answer session.